All right, so this is the question from 2016 on the BC exam, and it's number 6. And usually there seems to be a pattern on the BC exam. The last FRQ has to do with Taylor series, Taylor polynomials, this whole unit 10 part. So just so you can know what to expect. It says the function f has a Taylor series about x equals 1 that converges for all x in the interval of convergence, okay? It's known that f of 1 is 1, and the second derivative of 1 is negative 1/2, and the nth term, or the nth derivative of f at x equals 0 is given by this for all n's greater than or equal to 2. Okay. Write the first 4 non-zero terms in the general term for the Taylor series for f about x equals 0. All right, so I know the first 4 terms. The first term is f of 1, because it's centered around 1, plus f prime of 1 times x, plus f double prime of 1 times x squared over 2 factorial. Oh, I'm wrong. This is centered around x, or around x equals 1, right? So I'd write x minus 1 and x minus 1 squared. All right, plus the third derivative of 1 times x minus 1 cubed over 3 factorial plus dot, dot, dot. All right, so to find the general term, there's the first 4 non-zero terms, right? And I'll actually find the numbers here in a second. But to find the nth term, I would say, okay, it's always like the fourth term would be the fourth derivative of 1, so it's times x minus 1 to the nth all over n factorial. And I really wish I would have written smaller. All right, so this plus dot, dot, dot. That should be dot, dot, dot. Okay. So that's the general part, but it'd be times the nth derivative, right? But the nth derivative is given by negative 1 to the nth times n minus 1 factorial all over 2 to the n. And then I would say plus dot, dot, dot at the end. And I just ran out of room. All right, so first 4 non-zero terms, 1, 2, 3, 4, plus dot, 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 the general term, plus dot, dot, dot. Now she's finding the numbers. Okay, f of 1 is 1, minus 1/2 times x minus 1. Okay, now I actually got to plug in some numbers. I got to plug in 2 for the n to find out what the nth, or so the second derivative of 1 would be, right? So if I plug in 2, I get 1/4. It'd be 1/4. No, I don't. Yeah, I do. I get 1/4 times x minus 1 squared over 2 factorial, which is just 2. And then if I plug in 3, this would be negative. Plug in 3 minus 2 factorial. This would be 2 over 8 times x minus 1 cubed over 3 factorial. Plus dot, dot, dot. Okay, the nth term here. So to find the nth term, to kind of simplify that down, I think you could just rewrite it just like that. But I'm going to mess with it a little bit. This is going to be negative 1 to the n. Okay, I want the n and the n minus 1 factorial to be gone. So I'm going to keep the n minus 1 factorial on top. X minus 1 to the n plus dot, dot, dot. This is going to be 2 to the n times n minus 1 factorial. This is equal to n factorial. And that's the tricky part on this one. So if I wanted to rewrite this a little bit nicer, plus 1/8 x minus 1 squared minus 1/24 x minus 1 cubed plus dot, 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 negative 1 to the n minus 1. Oh, wait. The whole point of doing that was to cancel that out, right? So I'm gonna write that cancels, and I just have the x minus 1 to the n over 2 to the n times 2 plus dot, dot, dot. Okay, I think you'd be fine. You might want to check the scoring guidelines, but you should be fine with that because technically it's the same thing. All right, part B, the Taylor series for f about x equals 1 has a radius convergence of 2. Find the interval of convergence. Okay, so if the center is at 1 and the radius is 2, I'm going to add 2 to 1 to get 3, subtract 2 from 1 to get negative 1. But now I need to check, does it converge at negative 1 and does it converge at 3? So if I set x is equal to negative 1, okay, it's not working. I'm going to get, so go back up here. Okay, for some reason it's not working. Okay, so plug in 1, sorry, negative 1, I get 1. Negative 1 minus 1 is negative 2. Negative 2 times a half is plus 1. And then plug in negative 1 here. I'll get plus a half. Plug in negative 1 here. I get plus 2/3 plus dot, dot, dot. If I plug in negative 1 to this general term over here, I get negative 1 to the n. That would be negative 2 to the n over 2 to the n times n, which is just equal to this negative. So this is basically like negative 1 to the n, and then this part makes it another negative 1 to the n over n, which is just going to be 1 over n. So this thing is just a general harmonic that diverges. So I can say, I might say equal there plus dot, dot, dot. So that's all the same thing, it's just 1 over n. Now I realize the general term is 1 over n, so I've got this series 1 over n, and that diverges. All right, so when x is equal to 3, I'm going to plug in 3 up here for all the x's, and I get 1 minus 1 plus a half minus 2/3, and it looks exactly the same, but it alternates. So if I plug in 3, I should get negative 1 to the n times 2 to the n over 2 to the n times n, which is the alternating harmonic, which we know converges. So my interval of convergence, I don't include negative 1, but I include 3. All right, 2 more, and this is almost over. The Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. So I'm going to say f of 1.2 would be approximately equal to f of 1 plus f prime of 1 times 1.2 minus 1. Just plugging, I'm going to plug in 1.2 for x. Times 1.2 minus 1 squared over 2 factorial. Those are the first 3 non-zero terms. So I could say this is now equal to, or I can still say f of 1.2 is approximately 1 plus negative 1/2 times 0.2 plus 1/8 times 1.2 minus 1 squared. And that's a good safe stop. That would be an approximation. All right, last one. Show that the approximation found from part C is within 0.001 of the exact value. All right, so whenever I see this show that the approximation is within, that's either going to be a alternating series error bound, or it's going to be the Lagrange error bound. And I'm going to use the alternating series error bound because I have an alternating series. So the series is an alternating series because, I mean, it has the -1, right? So I've got to say, for the alternating series to work, the series is alternating. Alternating, that's how you spell it. With the limit as n goes to infinity of the non-alternating part. So I guess we can look at it like this part. Where is it? This part up here. So x minus the limit as n goes to infinity. Come on. So instead of x, I'm going to plug in 1.2 to the nth power over 2 to the n times n. That's equal to 0.2 to the n over 2 to the n times n, which is 0. The bottom obviously blows up. So it's an alternating series. The limit is equal to 0, and I've got to show, because I got to show that the series converges, right? I got to show that the nth term, or the n plus 1 term over the nth term, I got to show this non-increasing for it to converge, is less than or equal to 1. I'm just going to say that right now because I'm running out of time for the next class. So this is going to be less than or equal to 1, so therefore it converges by the alternating series test. So we've got to show that it converges, right? So you would just take this part right here. This is getting really sloppy, I'm sorry. Take that part right there, show that the n plus 1 term over the nth term is less than or equal to 1. And once you do that, you say that this thing converges. Since it converges, I know that the difference between the actual value of 1.2 and the approximation using the second degree, so the 3 terms of 1.2, is less than or equal to the next term in the series, or the next term in the sequence. And the next term would just be the third term in the sequence. So the third term was 1/24, 1.2 minus 1 cubed, which is equal to 1/24 times, okay, so 1.2 minus 1 is 0.2, and 0.2 is 1/5 times itself 3 times, which is equal to 1/300, which is less than 1/1000. And that was what would be required to show that the next term in the series, or the next term in the sequence, which we wrote down up here, that's the third one, or right here would be even easier, would be within 1/1000th. So I got to be able to convert this into a fraction, or just somehow, some way show that. All right, that's it for this video. Hopefully it helped, and thank you for watching. Bye.